We define the concept of mutual inductance between two elements as calculating the force, the flux in one element, and dividing by the current in the other. Let's look at an example. Suppose I have a wire, I1, and situated out here is my other element. This will be, if you like, element 2. So the wire is 1, and this is a very long wire. And according to our idea, this is equal to the magnetic field due to wire 1 integrated over element 2 divided by the current in wire 1. So how do I calculate this mutual inductance? Well, the first question I have to ask myself is, can I calculate the magnetic field from wire 1? And I look at the wire 1, and I recognize that this is a type of our Amperian geometry. It's just a wire, and we can assume it's a very long wire that I can get Ampere's law to calculate the field of wire 1. So I'll do it now. So let's pick a current, an Amperian loop, like that, radius r. Now, why did I pick a big loop like that? I want to emphasize that I'm trying to calculate the magnetic field in this region, which is going to go into the plane of the figure. And so I choose my Amperian loop. I pick my right-hand rule. This is not a Faraday law calculation. This is an Ampere law calculation. And I have B dot ds equals mu naught I enclosed. And here we have B times 2 pi r equals mu naught. All the current in this wire is cutting through, so that's I1. And I get my magnetic field B1 is equal to mu naught I1 over 2 pi r. So I know my magnetic field. It's pointing in the direction like this. And now I want to calculate this integral. Now again, it's not just B times the area. Why? Because the magnetic field is not uniform. It's falling off like 1 over r. So in order to calculate the flux through this area, I'm going to have to set up an area integral. Now I can do this area integral in the following way. What will I use for my little integration elements? And I'm going to draw that now. What I'm going to use is a little section of this area where this is dr prime. I'm going to give an integration variable, r prime. And if my whole thing is a height h, then my area element is just height times width. So I took a little strip. And you can see that for a very narrow strip, the B field is uniform. And so my mutual inductance is now just integrating. Remember, this is an integral over this object. We'll put the limits in a moment. It's the B field, which is mu naught I1 over 2 pi r prime, that's my integration variable, times h times dr prime. And what am I integrating r prime from? Suppose this edge is a distance s, and the whole object is a width w. Then going from here to there is I'm taking my integration from r prime equals s to r prime equals s plus w, and I have to divide by I1. And so what I'm just doing is adding up strips. Well, this is a straightforward integral. We get mu naught h over 2 pi natural log of s plus w over s, and that's the coefficient of mutual induction. Now, what's crucial to realize is that this is independent of the current that's flowing. It's just a property of the geometry of the wire and the loop. The i's are canceling I is producing the flux, and we're dividing by I. And that's how we calculated for this first example.